Okay. All right, so this is the fourth webinar for ECO-WES on water energy systems. Today's webinar is more focused on the policy and real-time and real-world case studies that show water energy nexus. Thank you, Jamie and Douglas, for being here. Jamie Ferro serves as Hazen and Sawyer's West Region Energy Management Lead, leading the execution of energy projects of all kinds for water agencies across the region, with over 20 years of experience in the water sector and a background in water law and policy, program design, project development, and project management. Jamie has spent the last 14 years specializing in energy management for the water sector. Jamie is also an adjunct professor at Chapman University in the Schmidt College of Science and Technology, teaching law and policy of water resources management and other environmental studies as requested over the past decade. Jamie is very active with the California Association of Sanitation Agencies on both the board of directors and as the chair of the engineering and research group. He regularly contributes his time to ECO-WES Task Committee as well as American Water Works Association's Energy Management Committee. Thank you, Jamie, for being here. Douglas O'Brien is a certified energy manager with 18 years of experience helping public agencies identify, prioritize, and implement energy projects. During his career in the energy sector, he has worked for the Ventura County Regional Energy Alliance, which is the first regional energy network in California, the Energy Coalition, which is the implementer of the Southern California Regional Energy Network, the Clean Coalition, which is an energy policy think tank and DER project developer, and West Yost Associates, which is a water engineering firm. Currently, Douglas is a program lead for the California Energy Commission's Distributed Electricity Backup Asset Program. He has experience in energy management, data analysis, financial analysis, competitive strategy, product development, and marketing. He holds a BA from Grinnell College and an MBA from Yale. Thank you so much, Doug, for being here. With that, we'll give the floor to Jamie and Douglas, and then I'm very excited to hear your presentation. Thank you.
As I mentioned, Douglas was going to set the stage a little bit with some discussion about the energy transition, the impacts of this transition on the water sector and what it means for our planning efforts and our implementation projects. And then I was going to dig into a couple of case studies where we're talking about really advanced energy resource planning and management for two different types of water systems. Are we all in agreement? Should I just proceed here while we work through some of the details in the interest of time?
Yes, let's do that.
All right. Well, thank you for that wonderful introduction. I know I wrote it, but the way you delivered it was very nice. Little comedy here, just kidding. Thank you. Oh, Doug, you're on mute. We can't hear you. I see your mouth moving. We're just going to go ahead and I'm going to present the first deck while you work through your tech. So Hazen and Sawyer, we're a full service engineering firm, all water. We don't do bridges, tunnels, roads, buildings. We just do water systems, and we do everything from master planning to construction management and everything in between. I've been with the firm for 2 years. And just really quick introduction, as I mentioned in my intro, 24 years in the water sector. The last 14 have been exclusively focused on energy in water systems. And when I got here to Hazen, I found a very mature energy management group that had been serving clients with energy management services in the water sector for about 25 years. So this is a well-integrated energy management group, and I'm in charge of the work that we do on the West region, but we work all across the country. So these are two California case studies that I'm going to present. The first, actually, I'll just really quickly here. The first case study here on the left is the Doheny Desal plant, and on the right here is the El Estero Water Reclamation Center in the city of Santa Barbara. So two coastal communities in very dense urban populations. Well, urban-ish, with not a lot of room to expand, very constrained footprints on both of them, and some very interesting water energy challenges that I want to talk to you about today. So the topic of my presentation here is integrated energy planning. The strategy here really what integrated means is, as you guys are all aware, is thinking about outside the boundaries of the water utilities infrastructure and really thinking about the energy grid as a very meaningful and important partner in how we manage energy. That integrated planning really does advance key agency priorities. It increases water affordability, enhances resilience, and advances community sustainability objectives when done right. And the key here with this little icon is connecting the dots. It's really thinking about comprehensive approaches and thinking about partners, thinking about opportunities. And as one of my old bosses used to say, burning down the box. Don't just think outside the box, but really burn down the box. There is no box. We need to really think about these strategies very holistically. So energy informed engineering, which Douglas is going to introduce in his talk, is really it's really and I won't steal his introduction to this concept, but it's really focused on driving the comprehension of energy, the importance of energy through all aspects of engineering work. And with our water sectors, we have to think about these various drivers that are really challenging, almost pushing water agencies to do much more with less. There's drivers that are both positive and pushing and pulling. So the positives would be, the opportunities for public-private partnerships, market opportunities. Some of the pushes would be regulatory and legislative drivers. Need to focus on enhance a public image, and again, integrating with other capital and labor priorities that the agencies, the water utilities might be facing. There's a lot of benefits to doing this. You guys can imagine, I know you're all clear, aware of these benefits, but thinking about the ability to make real comprehensive data-driven decisions and future-proofing our water systems, implementing energy projects with other strategic priorities. Think about just very simply think about the need to maybe consolidate meters at a facility, implement a battery solution in order to save money and in order to integrate with grid operations. Well, that project as a standalone initiative may have a 20-year simple payback ROI, return on investment, maybe even more, 30, 40 years. If you could couple that project with a strategic priority, say an energy master plan or, excuse me, an electrical systems upgrade or some sort of other capital project that's going on. You're mobilizing construction forces, you're mobilizing engineering resources to get a project done that you have to build for whatever reason, and then you integrate energy projects with it. You can improve the economics of an energy project and significantly advance some of those objectives that we've been talking about. So this is really where we think about holistic energy planning and energy informed engineering. So without any further ado, and I'm keeping my eye on the clock here, Doug. I'm going to wrap up at 9 at the very latest, okay? And that'll be a 30 minutes, and I think I can get through it quicker than that. Santa Barbara, City of Santa Barbara Water Resources Energy Master Plan, and then I'll close out with the Doheny Desalination Project. So before I advance and get into Santa Barbara, these are two very different projects. One project, Santa Barbara, is a long-range energy plan for a water utility, and the Doheny Desalination Project is a design build project for a 5 million gallon a day ocean desal plant in California. So this is part of, we're in at the 60% design phase with Doheny. We haven't built the project yet, but we've envisioned all of the interworkings that I'll be describing today. We're at the stage where the client, the South Coast Water District, is about to approve that start of construction, which is in this progressive design build. We get to the 60% design, and then we move right into mobilizing for construction. So the system is pretty well defined, but this is still a little bit theoretical at this point, but it's a useful case study, I believe. So starting with Santa Barbara, this is a case study on integrated long-range energy planning and utility coordination. So I'm going to give you a brief overview of the project, talk about the objectives of the client, what they asked me to do, discuss some of the outcomes to date and the opportunities, and describe how we're providing intuitive and interactive tools and why that's important in integrated energy planning. So you'll notice this little icon about the connecting the dots up top again. You'll see that pop up on a few screens, and that's not just because it's a pretty little graphic, but it's representing this concept of tying these multiple drivers and opportunities together in a way that's going to most impactfully benefit the bottom line of some of these energy projects. So let me just really briefly introduce you to Santa Barbara's water system. They manage a lot of utilities. Actually, we call it at the city of Santa Barbara, they refer to the four water utilities. There's the wastewater, the water utility, the desal facility, and then the water distribution system. So those four water utilities are how they organize themselves, sort of from a management perspective. But physically, they manage the Gibraltar Reservoir, which takes water from the State Water Project and the Coastal Branch Pipeline. Uh, uh, Excuse me, the Santa Ynez stores water in the Gibraltar Reservoir as well as water from the State Water Project comes into the Gibraltar Reservoir. That can be funneled down into Laurel Reservoir or over to Lake Cachuma, where it can also make its way down to Laurel Reservoir. So there's quite a bit of conveyance alternatives within their system here. A lot of that is dependent on rainfall, of course. And then they have the Ortega groundwater treatment plant and a series of groundwater wells in the lower zone of their community. They manage they own the Charles Meyer desalination plant. There's an asterisk there because that plant is operated by IDE, the Israeli desalination enterprise. That company manages the operations of that plant. So there's some complexities there. But they also have a recycle water treatment plant, which is what that picture I shared with you at the beginning, the El Estero Water Reclamation Center. They manage 300 miles of water system, 13 pump station, 14 reservoirs, pressure reducing valves, and over 27,000 metered service connections. So the master plan, this is just a brief overview of what we are working on with them. And this is the key here I want to highlight is this is a 10-year plan with a 30-year outlook. So Santa Barbara has said, give us a list of energy capital projects to implement over the next 10 years while thinking about the next 30 years. And had Douglas given you his presentation first, that concept would have had a little bit more context around it for today. I know you're all aware of this, but how do you predict what's going on in the energy sector, even in the next 10 years, much less the next 30? What does that mean from a delivery perspective for a client? I'm an engineering consultant. We have to deliver recommendations, not just ideas. We have to say, go build this thing in the next few years. So how do I make sure that I'm not going to be looked at as a team 5 years, 10 years down the road, say, why did they tell us to do that? So it's very tricky. And there's a lot of agencies in the neighborhood looking at how Santa Barbara is proceeding with this project and others. So starting from the bottom, we started with an energy benchmark baseline. How and where are you using energy? What are the flexible load opportunities? What is that market potential energy cost? How do we leverage existing CIPs, as I mentioned in the beginning? And then actually integrate it with capital improvement programs across the board and develop that 10-year energy plan, the Water Resources Energy Master Plan. You'll see that acronym from here on out, REMP, which I don't really like, but that's okay. We had proposed some really robust energy and data visualization strategies, which would then lead us along this 30-year path to a best practices throughout the organization, staff and partner engagement, and then long-term optimization. That's the goal. It is worth noting at this point that, and I mentioned this to many of you who have been in some of these discussions in either Anchorage or the previous discussion, the city of Santa Barbara has engaged with academic researchers for over a decade from Stanford University doing very rigorous theoretical exercises around water energy nexus collaboration and really focused on load management and flexible load management opportunities, primarily because in California, the grid is so constrained. And the real opportunities for water agencies in California is not cost savings from buying less power necessarily, but it's actually time of use is really the driver. And can we move the desal load off peak? Can we coordinate the wastewater plant and the desal plant together? Could we use a battery for arbitrage and load shaving? Those kinds of strategies have been really important. So for 10 years, they've been exploring these opportunities from an academic perspective. They hired us, and this is actually the nexus of this is working with some of these researchers in an environment like this with Tom and Douglas in the Energy Management Committee of the AWWA. They reached out to us and said, can you help us develop a master plan around this energy? We've done all this research. Now we want to implement. So that's where we're at. The objectives are really simple. I want to walk through these 5 objectives. Maximize financial and resilience benefits, expand renewable and energy and battery energy storage systems. They've got some of these systems already. Enhance energy resilience and reliability, integrate research initiatives, as I just mentioned, into their capital plans, and design an adaptive and dynamic plan. And this is really one of those keys of meeting future uncertainties through this adaptive and dynamic nature. So the outcomes, and I'll walk through just really briefly where we're at, and then we'll talk about some of the technical work. Baseline energy use documentation. They really just, for a moment, this is their first energy master plan, and they've done a lot of energy work, but really documenting where they are, where and how they use energy throughout this very complex system. We then developed a Microsoft Power BI based dashboard for them to slice and dice the data, look historical, look at different rates, some counterfactuals about if we were on a different rate at this plant, how might that have affected overall cost in a period of time. At the moment, this is a static snapshot in time. It's basically taking that baseline information and putting it into a format where you can slice and dice much how Power BI is intended to be used. That's where it's at today. We're in the process of actually integrating some real-time upgrades into this dashboard right now where they can regularly refresh the data and see near real-time energy use information throughout their system. The next task here, what we've accomplished is help them prioritize these energy opportunities in different projects and integrate those energy opportunities with those other city priorities in a digital deliverable format that's interactive and intuitive. So not just the dashboard that you can slice and dice, but how do the capital projects stack up and how might things change as priorities change? If solids handling, sludge disposal costs go up, is there something you might change? If energy costs go up, if Edison, Southern California Edison implements dynamic real-time pricing instead of static tariffs that they've been using for a while with standard time of use rates, how might that change the economics of some of these projects? So we want to create this dynamic environment where they can make these global changes in assumptions and not have to redo the master plan. I'll talk a little bit about that as I kind of close up this case study. Ultimately, again, 10-year energy project planning strategy with 30-year planning outlook. Put an asterisk on there. We are in the last few months of wrapping up this entire plan, so we haven't quite given them that full deliverable yet. What are the projects we're looking at? What are the priority opportunities? There's 87 individual energy projects that we have evaluated throughout the utility that come anything from energy efficiency projects, self-generation to load management strategies. 87, 86 projects. How do you prioritize those projects? And how do you make sure that you're really driving towards biggest bang for your buck implementation work? We prioritize a couple of areas. The key here, these you notice down here at the bottom right of my screen, the desal and the recycle water facility are on the same property, separated by a street, but on the same meter. So obviously, there's a lot of opportunity there for load flexibility and coordinated operation of both desal and water resources recovery facility. Coordinate the use of those, optimize the performance of the batteries that are on system, combine we need to separate the load from each of these two facilities, but how do you time when and how some of the implementation, some of the operations of each of these facilities actually pulls load from the grid. And I'd like to just note that one of the researchers actually has just joined us. He's been really instrumental in supporting this client for this city for many years as in his role at Stanford. So hello, Akshay. Hope you're doing well, man. Next big opportunity here is the meter consolidation and microgrid at the Cater Water Treatment and Laurel Reservoir. There's a hydro facility there. Interestingly enough, as I mentioned with the desal and recycle water, that's on 1 meter from the utility. Well, up at Laurel and Cater, there's actually 4 meters there. So we've got a main plant meter, an admin meter, a pump station meter, another pump station meter, and then just across the road, there's a hydroelectric facility on a Southern California Edison power purchase agreement generating hydroelectricity. So how do we think about all of these opportunities there and really, do we consolidate all those meters into one? They've considered floating solar over the years. So really there's a big opportunity with this treatment system to optimize the performance of the system on the grid. And then a couple other at the wastewater treatment plant, comprehensive biosolids and energy strategic plan. There's aeration improvements in there. And then piloting right now a wastewater influent equalization and secondary effluent return pump optimization strategy. That is a mouthful. I didn't realize that one bullet was going to be so hard to say. The idea is thinking about when you can't really control what comes into a wastewater plant and when, or can you? In this case, we've seen a lot of water conservation in the area, so they have very high strength sewage, but actually quite a bit of capacity within their system hydraulically. So what we're working on with them right now is how do you use that water system to, from a loading perspective, to manage the load, not the hydraulics, and use the hydraulics of the system as essentially a thermal battery. We could time some of those recirculation strategies. We can actually back up the collection system while keeping that sewage fresh through mixing and bioaugmentation strategies and figure out when is that load going to hit the blowers, which is where the real energy load at that treatment plant is. And so we're working on some of those strategies. And again, how might that be coordinated with the battery or with the other existing loads on site? And the final piece of work is really has come out of that years of Stanford research is focusing on targeted leak loss repair and pump sequencing reservoir control strategies. So if we know the energy intensity of the system and we know that most water agencies, including Santa Barbara, are systematically repairing leaks in their system, where do we focus our efforts on existing leak repair strategies? Target those where you have high energy intensity and high flexibility, both in the pumping and the targeted leak repair. So we ended up uh, presenting this multi-criteria decision analysis framework where each project, we could think about the economics, the return on investment of an energy project just from a financial perspective, but there's other non-monetary benefits to each one of these projects. So we developed this criteria ranking strategy where you've got different scores for each of these criteria and then a weighting that is attached to each one of these criteria. So that each one of the utilities might have slightly different weights for the different criteria. And the goal is to score each one of these measures. And so just looking at this is just for the wastewater plant. There's these four super measures, we call them, with each one of these sub measures below them. These are the kinds of opportunities we're looking at. You could see on the right-hand column the total benefits and different kinds of monetary and non-monetary benefits. So you really start to think about how do we connect some of these strategies with other agency priorities. This is not meant to be a detailed discussion, just to share how are we going to integrate these energy projects that are here in the middle of the screen: blower automation, joint meter evaluation, aeration improvements, integrated biosolids and energy plan, influent EQ strategy, and biostorage. How do we implement those projects with the other along the bottom? These are their ongoing existing capital priorities. Some of them have to do with an additional load on the grid. If you look all the way, digester upgrades produce more biogas, so that might actually reduce the loads. So any of these capital priorities may have a very significant impact on energy use and time of use of energy and the grid. And so we want to make sure that we are working together with the city to time the implementation of these strategies in a way that really makes these projects make the most sense. At the end of the day, do we deliver a big document that can sit on a desk or on a bookshelf and collect cobwebs? Typically, this is how our industry has delivered energy master plans. Even the word master plan is out of fashion these days. We have transitioned to calling them energy management plans instead of energy master plans. But traditionally, a master plan is a big document with all the technical memos and all the ideas. And the moment you publish it, just like a new car, you drive it off the lot, it loses value because the real-time conditions are changing all around us. Our approach is to develop an integrated energy plan that ties all of these things together, considers these external factors, and ultimately delivers an actionable, intuitive roadmap of how these projects and capital priorities fit together. So that was the Santa Barbara case study, right on time. I've got about 15 minutes to jump into the next case study, and hopefully we'll be able to get Douglas to give us that overarching context, and then we can have some discussions about these projects. South Coast Water District here in my neighborhood. This is actually near and dear to my heart. I've known about this project for about over 15 years. This project has been on the books. It's been this project has been contemplated for nearly 27 years. And this project, this case study represents a very comprehensive energy portfolio. Here's that graphic of the connected dots up top. Maximizing cost, eliminating greenhouse gas emissions, and maximizing resilience. Those three alone, if you were asked to do just those three things, you would think, how am I going to possibly optimize for all of those variables? I'll give you a brief overview of the project, talk about some of the challenges. We'll describe the energy requirements of the very intensive the energy intensity requirements of this desal system, talk about the opportunities, and I think I'll leave you with a couple of resources. It's worth noting before I move on, as I said at the beginning, this is a progressive design, build, own, operate, maintain procurement. So we call that DBOOM. It's like a progressive design build with a few other tweaks to it. So the Doheny Desal partners will actually own and operate this system financed by the public utility for a period of 20 years until we transfer that ownership back over to South Coast Water District and their partners. So lots riding on this project, and there's a lot of risk, and there's a lot of risk sharing between this progressive design build strategy with the client. So Acciona is the world's largest, well, not, no, they're the number one ranked desal company. They go back and forth with IDE every year, but Acciona, this last couple of years has produced more desal water. I don't know how the ranking works, but it is the number one desal company in the world right now. Freelance is a local water-focused contract construction firm, down here based in Escondido, and Hazen is the engineer of record on this project. So the South Coast Water District, situated right here between Los Angeles and San Diego and South Orange County. This is the third desal plant in California. I talked a little bit about Santa Barbara's a second ago, and then you may have heard of the big one down in Carlsbad, 50 million gallon a day plant. The first year of operation will be 2029. We break ground next year on some well pumping, some well prep work, and the plant will start construction 27, and then we'll be serving water to the community by 2029. So this is intended to be a resilient, local, and reliable water supply for the community because South Coast Water District imports 85 to 100% of its water for the community from Metropolitan Water District, the wholesale water agency in the area. Very reliant on imported water, high risk. If something goes wrong, this entire community is out of water. So this is a necessary solution, which is why it's been contemplated for so many years. The challenges we face on this project are pretty significant. As you know, desal is very energy intensive. You have to push water through a membrane. At the same time, then, the California Coastal Commission has put on a special condition to issuing the coastal zone permit that the energy supply must be net carbon neutral. Wow, that's going to be a tough one in that area, and I'll show you the site a little bit. The site is very constrained. We can't build a bunch of solar. We can't build a bunch of battery banks on site. We will, as you'll see, we have designed those solutions, but we can't offset the entire load on site. The grid is constrained as well in the area. So it is not feasible or economically feasible to import power from distant solar fields, farms, utility scale solar farms, or wind farms in Idaho, because that will not provide a resilient backup power supply source of power when there's interruptions in the grid. That would not accomplish the resilience goals that the project aims to achieve. And reducing the cost of energy is a major driver. SDG&E, the utility in the area, has the highest energy rates anywhere in the United States, and it's not looking like it's going down anytime soon. The sustainability pillars, and I used that term sustainability, the Coastal Commission didn't, of this project are really fourfold. And so just worth introducing these four concepts briefly besides the energy ones. This is that reliable local water supply. The Coastal Commission has also required an ocean intake slant well. So the water will be pulled from below it's subsurface ocean groundwaters, not directly pulling water from the ocean in with benthic intake and marine life impacts. It actually is drawing ocean groundwater, which is a little bit less salty, has some other constituents in it, but it is still salt water, and it is very energy intensive, less environmental impacts from the intake. And then the outfall, the RO concentrate, is actually blended with the neighboring agency's wastewater discharge, and it again minimizing the impacts of the ocean discharge to the environment. And finally, the net carbon neutral energy supply. That is still under the staff report is the California California Coastal Commission staff is still uh, waffling a little bit on what the actual definition of that requirement means, but we will work our way through that over the next few months and years. The question we were asked then is how do we meet the requirements of the special condition while minimizing the impact on the cost of water? We developed a four-tier strategy, on-site and off-site strategies, and I'll talk to you a little bit about each of these and how we manage this load within the constraints of the grid. The energy usage is pretty significant. We're looking at 28 million kilowatt hours a year, almost 29. Total power installed is 4.1 megawatts. The peak demand, 3.8 megawatts. We're looking at estimated energy cost, assuming 100% grid power, about $7.3 million. Carbon offsets to meet that carbon neutrality or the green, the net carbon neutral energy supply requirements would be about $320,000 of carbon offsets, and the estimated cost of energy if we just receive power from SDG&E is about 26.5 cents a kilowatt hour. So that's important because, as you probably all know, a solar project even, and a battery system can compete pretty well when you're looking against a baseline of 26.5 cents kilowatt hour. So that is working in our benefit. But at the end of the day, this project will not move forward if we cannot lower those energy costs below about 20 cents per kilowatt hour. Actually, we think we need to maybe get closer to 17 cents a kilowatt hour. So I'm going to talk to you about our journey to get there. Tier one, really focus on site. Let's reduce the amount of energy that we need for the system, recover as much energy as possible. Ultimately, the goal there is to minimize the purchase power from SDG&E. We've got all the typical desal facility strategies that you might imagine. Energy load management, thinking about when and how we use energy, energy efficiency, design flexibility with both the pretreatment system on VFDs throughout all the pumping loops within the plant, and variable production schedules to make sure that we minimize any of those time of use charges. The on-site energy efficiency, digging into these energy recovery devices, these are standard issue within any desal facility, but it does capture a lot of that hydraulic energy. When you pressurize these RO vessels, what do you do with that pressure? Capture it, return that pressure back into the feed loop. Therefore, you don't have to continually just blow off pressurized water, pressurized energy. And then using those VFDs and those slant wells is obviously a pretty standard energy efficiencies tactic for the site. Tier two is where things get exciting, and that's where I would like to spend the majority of the last few minutes here in this case study. We've envisioned a microgrid, and I'll talk a little bit about the elements of that strategy here. So the first priority is to maximize the use and value of solar and battery storage. Once you've purchased those assets, the solar's free, no fuel required. Priority number two, let's offset those electricity purchases with lower cost natural gas. And a secondary benefit would be integrating all of these on-site strategies with our standby power strategy. There was envisioned a 4 megawatt diesel generator on site for power interruptions, and we've been able to avoid actually purchasing that diesel generator to offset the emergency standby requirements here. We've got about 3.2 megawatts of rooftop and ground-mounted solar. We've got a 4-hour battery, 2 megawatt 4-hour battery storage system, and 12 linear generators envisioned for the project as it stands today. These linear generators are 250 kW rating each, so about 3 megawatts of linear generators. That will supply 50% of the load and provide for safe shutdowns during power outages. And as I mentioned a second ago, eliminates the need for a standby generator. So not an insignificant strategy here from a resilience and cost-effective point of view as well. The megawatts, the 3.25 megawatts of solar and battery estimate about $1.2 million of annual savings for the facility. So that in itself is really a big benefit to the project. Is maximize. We don't have a lot of room, but we've used as much of the footprint as possible, and all of the buildings where possible in the desal facility are designed with roof mounted facilities. The linear generators, if you haven't heard, are quite a significant innovative technology that's really getting a lot of traction in our industry. This is a state-of-the-art. Basically, it's a gas generator with few moving parts. It's fuel agnostic. You can switch between natural gas, renewable natural gas, biogas, hydrogen in the future, could even run on ammonia. So it's a very low, there's very few moving parts and a very high efficiency conversion of natural gas to electricity. What it also provided us was that redundancy. If the grid goes down, the linear generator, it's not likely that the electricity grid and the natural gas grid go down at the same time. So we have a lot of interesting redundancy and opportunities to optimize there. The profile of the facility, you can see this on a daily basis. It's relatively flat, and that is because of that load management strategies that we built into the load list. So you could see all the different equipment at the desal facility. It would not necessarily just have a flat operation, but we've programmed most of the operation. So there's a little bump in the middle of the day when most of the staff is on site, and power is still cheap. So that's our flat, consistent load profile that we've envisioned. And then this bottom line here, this green line is the 12 linear generators, which will offset as a base load. They'll offset to about 2 megawatts of that base load. And then you could see the dark blue line that dips here. This is the solar. Sorry, this is the battery discharging in the middle of the day. And then, no, I got that wrong. That's the solar reducing the load from the grid. And then the light blue line here is the batteries discharging. What's left over is this black line is what we're actually purchasing from the local electric utility. The last interesting piece that I'll share here with you is the slant wells that are off-site. We're actually electrically connecting those slant wells to that main load at the desal facility so that we can take advantage of all of the renewable energy and the natural gas linear generator energy to supply that that slant well load at an offsite facility. So while we're connecting the facilities, obviously you need to pump the desal, the ocean water up to the treatment plant in that same master, that tunnel. We call it the micro tunnel pipeline. We have run two 6-inch conduits to feed medium voltage power to that switch gear at the pump stations so that we don't have to run a separate utility source to that pump station. There's three 350 horsepower motors on the beach there and another one standby. So quite a significant load that can be powered by distant, it's about 2,000 feet away, that desal facility energy infrastructure. The last piece I'll touch on here in closing is, as I mentioned, those linear generators are fuel agnostic. We had envisioned some other solar facilities, battery facilities at reservoirs and admin buildings, pump stations throughout the service area, maybe even some inline power opportunities and working with some of those partner agencies on some of these strategies. But the real opportunity comes with the landfill gas. The neighboring agency, actually, the Orange County Waste and Recycling runs a landfill, which is only about 8 miles away from the desal facility. There are some natural gas pipelines in the area. And we've considered a variety of landfill gas to RNG, renewable natural gas into the pipeline. We've actually considered virtual pipeline strategies of trucking landfill gas down to the plant. Ultimately, in several years, when this landfill gas is available, we'll transition that natural gas in the linear generators over to a landfill gas and actually continue to reduce the cost of operating and reduce the need to buy some of those carbon credits to offset the natural gas load. So the final piece here is purchasing those carbon credits. Again, we have to purchase somewhere between $500,000 and $860,000 of carbon credits if we were just buying all the power from the utility. That is a really important driver, is figuring out how to minimize the purchases of RECs. At the end of the day, this is my closing slide here. We started with $7.3 million. With this optimized energy portfolio and strategies of working with the utilities, the local gas and electric utilities, we're down to about a $5 million a year annual energy cost. We've got our cost of energy down, including carbon credits, to about 18 cents a kilowatt hour from 26. And we've got a very diverse portfolio of energy supplies coordinated with both the gas and electric utilities. We've eliminated the need for a 3 megawatt diesel generator. All of this has taken about an additional $24 million in capital projects. If you look at those energy projects as standalone capital investments, it's about an 11-year simple payback period. So for a 50-year project, most of these water infrastructure utilities consider 35, 40, 50 years expected useful life. So an 11-year simple payback return on investment is not a bad deal. The overall project's about $250 million. So we're adding a not insignificant amount of capital, but to accomplish these goals, we're recommending that the agency moves forward with a capital improvement instead of some public-private partnerships leasing some of this equipment. So I am right on time. If looking forward to questions, this was supposed to be our closeout slide, so we'll hopefully Doug can get on now and share his screen. But I'm really looking forward to talking to you guys about any questions you might have, and thank you again for the opportunity. Good luck, Doug.
So, thank you. Uh, Saki, I sent you a copy of the deck. If you could bring it up. Yeah, let's go ahead to the next slide. So today we're going to talk about the energy transition, what it is, how it's progressing. We're going to talk about the stresses that are coming onto the electric grid, primarily from climate impacts and demand growth. We'll talk about distributed energy resources. We're going to talk a little bit about innovation and transformation, and then we'll talk about advanced energy management for the water sector. Next slide. So I'm sure you all are familiar with the term energy transition, but have you really considered how an energy transition relates to civilization? Next slide. The definition here is a pretty standard one, but how we use and interact with energy is dependent on the direct energy source that's available. Throughout history, we have continued to expand the range of energy resources that we use. Every expansion has been accompanied with technological developments that enable us to effectively utilize the energy resource. Consider the ox and the plow, the coal and the steam engine, petroleum and the internal combustion engine. Sakya, why don't you tap forward a couple of times? And each energy transition marked a significant transformation of human society. So, Sakya, can you tap once on the forward? It's a transition. Am I even here? Oh shit, I dropped off. Wow.
Is
We
it
can still
correct?
hear you,
Oh, you can
Douglas.
still. Oh, okay.
Slide still there.
There we go. Can
Is
can you
this
tap again on the
one?
slide, Sakya?
This one? This is what I have.
Okay. I'm looking at. What am I looking at here? All right. There we go. You know what? I can't see where you are. Let me fix something here.
Transition is started.
Okay, there we go. All right, now, no, go back. I'm sorry, back. All right, stay there. All right, the ox and the plow marked the rapid expansion of the agrarian culture. Coal and the steam engine launched the Industrial Revolution. Petroleum and the internal combustion engine drove an expansion of the transportation and electrification, which transformed highly regional economies into a supercharged regional economy integrated to form the modern global economy. Each of these transitions is also marked by major wealth generation. Recently, you may have heard that the energy transition is not happening or it's stalled, and the evidence that's pointed to support such a notion is that the use of oil has continued to increase over the last decade. And this is true, but it's not the whole picture. So next slide. This slide is a global representation of the new energy resources that are coming online. And as you can see, there's a steady decline of the fossil fuel assets that are coming on each year and a steady increase of renewable generation. Next slide. This slide is focused on the United States. Hold on a second. I need to be able to see where you guys are at.
Bar graph.
Oh, sorry.
Says the transition has started. Annual
Yeah.
net change of U.S.
I'm
electric
just
power
bringing this
sector.
over to the other screen. Yeah. All right. So this graph shows the United States, but it adds the additional details. As new ones are coming online, you can see old fossil generation resources are dropping off. And the reason this is happening is because since 2023, it is less expensive to build a new renewable and battery generation facility than it is to continue to even run an existing coal plant. Since 2021, it has been less expensive to build a new renewable battery renewable and battery facility than it is to build a new gas generation plant. And based on the fact that gas prices are likely to be going up over the next 5 to 10 years, we will soon see that it's less expensive to build a new renewable and battery facility than it is to even continue to run an existing battery power plant, gas plant. Next slide. This is an interesting graph that popped up on my feed just last week, and it shows that in 2024, we actually added more renewable solar and wind than there was compared to an increase in demand at the global scale. Next slide. This slide shows that the banking industry, the finance industry, is now making more money from green projects than they are from fossil fuel projects. They're still making a huge amount of money from fossil fuel, but it is evidence that the transition is moving forward. Next slide. We are at an inflection point, and to help you appreciate just how significant the current trends are, I want to share some of the most telling comments made by Darren Woods, CEO of ExxonMobil. The CEO of the largest fossil fuel company in the world has said that by 2040, all new passenger vehicles sold worldwide would be electric. Now, given the headwinds that we have here in the United States, we might need to modify this and say that by 2024, all new cars will be electric, except for North America and perhaps Europe. But what's more important is he even indicated directly that as we move into the future in the next decade or so, their product will no longer be primarily focused on energy, and that their product as an energy resource is going to be in decline. And they're going to pivot and focus more on the other products that gas and oil can provide, like fertilizer and plastics. Next slide. All right, we're going to shift over to grid stresses. And first, we're going to focus on climate events. Next slide. This graph shows the billion-dollar storms that have hit us, and you can see that there's been a steady increase year after year. Over the last 40 years, we've seen a steady increase of the extreme climate events driven by a warming climate. These events are causing enormous damage to property, infrastructure, and the economy. The electric transmission and distribution system are not immune to this devastation. You may be accustomed to hearing that the renewables are the reason for the majority of the cost increases, and this is false. Right now, most of the increases that you're seeing in your electric bill is costs incurred to recover from climate disaster and the grid hardening work that has to come afterwards. One of the really disturbing things that's come to light is the disaster recovery industry is now making up 3% of our global domestic product. And Wall Street has taken notice and is investing heavily in those industries. Forward. I chose California to show the trend of rapid rate increases from 2013 to present because they're sort of the poster child. I didn't want to use the average trend across the country because it really doesn't tell you what's going on. Why don't you tap forward to the next one? And the reality is that depending upon where you are in the country will determine what your rates are and how fast those rates are escalating. But most of these rate increases are due to climate impacts. But there's also the other side, which we're now going to move on to, which is demand growth. So why don't you tap forward? So there are multiple dimensions to demand growth that the water facility needs to consider. There's the grid-wide demand growth, there's local circuit substation demand growth and capacity limits, and then there's the facility demand growth. Tap ahead. So on the national level, we've got the move to electrify everything. We've got reindustrialization efforts, EV and EV charging infrastructure, and then, of course, data centers. And at the local level, water demand growth for advanced water treatment and nutrient removal. Whenever there is a demand growth, there is a reasonable expectation that for the short to medium term, there will be some price increase and then the prices will retreat. But it's also true that when the expansion comes, prices for energy can go down. And in fact, a recent report by Lawrence Berkeley National Labs has shown that grid scale renewable deployed via market incentives has actually lowered the energy cost component on your bill. But the same report states that very clearly that similar outcomes in the future is not guaranteed. And the reason is that investor-owned utilities have a strong incentive to meet demand growth in the most expensive way they can find. For them, expensive, big capital projects means more profit. So unfortunately, this demand growth crisis that we're in right now is an opportunity for the IOUs to fast track projects that are in their best interest and not in the best interest of the ratepayer. Next slide. As an example, we'll talk about PJM. They are a regional transmission operator for 13 states in the District of Columbia. They have the highest concentration of data centers, and they are center stage for AI. And PJM wants to fast track new gas generation to meet this demand. The way the regulatory framework is set up is that it's supposed to ensure that when new loads come online, they should pay for the generation and grid upgrades that need to come to support them. But unfortunately, over time, the vertical integration of the IOUs and the transmission systems have given them sway over the process, the regulatory process, and more often than not, they end up getting to do what they want and improve their bottom line. And we, the ratepayer, are the one who have to foot the bill. Even their PJM's own market monitor has warned that if we don't make the new loads pay for the rate increases, it's all going to fall on the ratepayer to the tune of some $5.48 billion in just their territory alone. Now, the irony, go to the next slide. The irony is right now, sitting in the queue, waiting for an interconnection pathway is 2.5 terawatts of new generation. Most of that is a combination of wind and solar combined with batteries. That is twice the amount of capacity that our entire grid currently has. So think about that. We've got 2 times what we currently are able to deliver to the grid waiting to connect. And their connection process has been stymied again because of the vertical integration and the control that these large corporations have over the regulatory process. So let's go forward to the next slide. The grid reliability and cost crisis, I'm not making it up. I mean, there are multiple organizations have called this out and are raising the alarm that both the reliability of our grid and the costs are getting out of line. There's one item here on the Department of Energy that I want to make a call out to, and we'll come back to it in a little while. This DOE report came out in July, and it is a creature of our current administration. This represents a complete 180-degree turnaround for the Department of Energy. And we'll talk more about this, but essentially the program that they're saying they need to put in place, in my view and many others, will actually bring on the very blackouts that they're claiming they're going to try and prevent. Next slide. So I'll talk a little bit about distributed energy resources. I'm sure many of you are familiar with it, but I just want to cover the ground about what they're all about and how it's had an impact on our grid infrastructure. Next slide. Prior to the growth of renewables and distributed energy networks, energy systems, energy flowed in one direction. You had a generation source, and the energy was pushed out to the edges where you metered what would be recorded and used at the end site. Now, energy moves in both directions, and importantly, the energy provided by DERs out on the edge can fluctuate, and sometimes dramatically, which causes dangerous voltage and frequency disruptions. This was a significant challenge for the distribution operator to figure out, and California is a great example of how successful they have been at adapting to this new challenge. Next slide. So the federal government has recognized the vital role that distributed energy resources are going to play in the energy transition, particularly for providing resilience and, in the long term, provide substantial contribution to reliability. They also recognize that without substantial incentives and new market rules, it's going to be hard for DERs to scale up. So the federal government established FERC Order 2222, which does 2 things. First, it defines what distributed energy resources are, And that list includes energy efficiency and demand response, which is a very enlightened position for them to take. And those are energy management practices that water facilities already have experience with. The order also mandates that DERs must be allowed to participate in the energy markets on a level playing field and be fairly compensated for the services they provide to the grid. Water and wastewater facilities, due to their load profile, have a great opportunity to participate in this market structure. Any investment made in building energy infrastructure now will provide real economic benefits in the future. Next slide. So I just want to, emphasize again, I'm not just saying this. There's lots of evidence, lots of research that are demonstrating that renewable energy has become the least expensive alternative for new energy infrastructure, whether it be on the bulk grid or on the distribution system in front of the meter or behind the meter. And DERs are the best investment to provide resilience and mitigate against the impacts of extreme climate events and to control energy costs. Next slide. So DERs are a tool. The DERs are a tool to manage your energy needs and constraints. DERs help contain and reduce energy costs. DERs are a valuable asset to have during emergencies. And DERs facilitate participating in energy markets and grid events and get compensated for that participation. Next. All right, so we're going to talk a little bit about innovation and transformation. I hope at this point you recognize that technologies for renewable energy and distributed energy resources are mature and that you can depend on them. But I also assume that some of you still have some skepticism about the bigger picture of the energy transition and the rush to electrify everything and be fossil free. And you're justified to have some of that skepticism. But let's take a minute and talk about innovation. First, innovation is tightly correlated with energy transitions. Each time we've had an energy transition, there has been a dramatic increase in innovation across all sectors of the economy. But most importantly, innovation is not just about the technology. We innovate in every facet of our society. New technologies emerge, and there's always a need to innovate on policy, legislation, regulation, and redesign our infrastructure. 100 years ago, when Henry Ford introduced the Model T, no one knew that we would end up with a car practically in every driveway. And all you have to do is look out the window, and for better or worse, you see a world that has been designed around the automobile. And think of all the innovation, technology and regulatory infrastructure, legislation, policy on all of that innovation has aligned right back to the Model T. 100 years ago, nobody thought that once Thomas Edison started stringing up wires, we'd end up with over 200,000 miles of transmission lines with electricity being pushed over those lines from jet engines. And again, think of all the innovation that's gone into that, both technological, but also legislative, market design, regulatory infrastructure, policy, all of that having a link back to that first effort by Thomas Edison to start electrifying things. I can't predict the future of what this energy transition is going to do. And why don't we go to the next slide? But I want you to consider, when I first did this version of the presentation, I cited several initiatives that were going on. So Peninsula Clean Energy announced a couple of years ago that they were going to have 100% 100% clean energy for their whole constituent base, and that they'd get there by 2028. And they are on track for that. Another interesting one that popped up was Microsoft saying that they entered into agreement to receive 1 megawatt of capacity from a fusion reactor in 2028. And they're not the only ones who are looking at this right now. So it sounds like fusion energy, sustained fusion energy, has been achieved, and we're just waiting for them to set up the fuel supply system so they can actually turn these generators on and make them run. But another one that I pointed out was that GM said by 2028, they would have the cost of a battery down to $85 a kilowatt hour. And I immediately thought to myself, that's amazing. I have 2 Tesla Powerwalls, and For the batteries alone, not the inverter and not the gateway, but the batteries, it was $7,500. Now, at $85 a kilowatt hour, you can get those two Tesla Powerwalls for the price of a high-end refrigerator. But now here we are, where Catal, a Chinese battery manufacturer, has announced that their sodium-ion battery are currently at $19 a kilowatt hour, and they expect to get that down to 10. So again, for just the batteries, not some of the hardware and installation costs, at $20, that's $540 for two Tesla Powerwalls. And at $10, that's $270. And I want to emphasize, it's going to take some time for those prices to actually be available in our market for stationary storage for home use, but it's going to make batteries a household appliance. In California, you may not be aware, right now, we operated our entire grid on 100% clean energy for 1,824 hours. That's the equivalent of 76 days, 24/7 of clean energy, or 5.5 hours a day. Thin film solar has achieved a new efficiency in the laboratory at 30%, which is absolutely amazing. And right now, thin film is about a third the price of standard, but its efficiency isn't anywhere compared to what we have. But if this new generation comes out, and it will also be about a third of the cost of traditional solar, that is a huge advancement. One of the things that's happened here in California since I first did this presentation is our Title 24, our energy code, has shifted over to the next level. And now all new construction in California for homes, multifamily and single family, it is mandated that they have solar energy. The next iteration is probably going to mandate that they also have batteries to go along with it. So again, solar is going to become a standard part of our infrastructure and our residential and commercial build out as we move forward in time. Batteries. Again, in California, batteries are carrying 25% of the evening ramp. And this is a transition that went from just 1% in 2022 to 25% now. So you understand the whole duck curve. And as solar goes down, gas plants have to ramp up very quickly. Well, here in California, batteries are carrying 25% of that load, and they will probably hit 50% by 2027 or 2028. In China, this is a big one. Gasoline consumption has moved into structural decline because of the rapid pace of EV adoption. And there are massive developments in HVAC that are going to yield significant energy reductions, and we should start seeing those rolling out over the next decade. Now, as I was doing research to find, these kind of innovative things that are dropping every day, I also came across a number of things that made me realize that we are at a new point in the energy transition. I call it the mid-transition. And on this graphic, it's phase 3, regime struggle. We are getting pushed back by the old regime of energy resources and their special interest groups. And as evidence to that, I point out how our current administration is working very, very hard to force coal plants and gas plants that are scheduled to retire to stay on and keep running. And that report, the report that I pointed out earlier, it's evidence of their intent to not only promote the old generation assets, but also push down and restrain the deployment of renewables and batteries. And the other big thing that they have done is lift the prohibition on the export of liquefied natural gas. All those things together are guaranteed to raise costs for the ratepayer right across the country. All right, let's move on to the next slide. So the case for DERs and Advanced Energy Resource Management and Planning. Next. I had AI generate this. Did pretty good job, maybe a little overkill. You can see here that, based on everything I've said, we are in a crisis. There are increased constraints on the grid, higher costs, less reliability, and water and wastewater facilities really need to have a paradigm shift in the way they think about energy. Next slide. Tap forward once. So when Jamie and I were working at West Joe's Associates, we were introduced to a concept called cyber-informed engineering. And it basically it says, for water agencies, you can't just assume that your IT guys are going to provide you with cybersecurity. Go ahead and tap forward. You have to accept that the hackers are going to get in. They will get into the system. Operators must be able to quickly isolate the system from the hacker's control and be able to continue to operate the system. So this was a paradigm shift where they had to accept, all right, wait a minute. We can't just rely on IT to provide us a service. We've got to be prepared to take control of the system because the hackers are going to get in. Well, when it comes to energy, I think there's a similar mind shift that needs to take place for a majority of the water operators. Now, Jamie's was talking about what's going on here in California. And I think, again, California is kind of the poster child of what's going to happen to the rest of the country. And so a lot of the water operators here are kind of already into that curve. They're already seeing that they have to take more ownership and command of their energy resources. So during one of the conversations Jamie and I were having while we were at West just about this topic, why don't you tap forward? I decided that I was going to co-opt that idea of cyber-informed energy engineering and come up with a framework for energy-informed engineering. And I won't bother reading through this. I'll let us get into questions. But Jamie's presentation is basically a roadmap on how you can use the principles of energy-informed engineering and integrate advanced energy management and energy resource planning into your capital design. So that's it. Let's open it up to questions. If anybody has any.
Thank you so much. I know that Jamie has a quick, has a hard stop. So I don't know, Jamie, do you have 1 minute or no? You
Yeah,
have to
2 minutes. Yeah, no problem. I
There are
really do
two
have,
questions
yeah.
for you in the
Okay.
chat.
Okay, go for it. I don't see them, but yeah.
So given the high risk of wildfires, does the master plan specifically account for the fire flow demands and the infrastructure required to support them?
Absolutely. Yeah, that's job number one is making sure they can keep the water flowing. We have some pump stations where we're contemplating batteries, out in that by the water treatment facility. There's some pump stations that provide fire flow, so they've already got backup batteries there. Thinking about that. Thank you. Great question.
Mm-hmm. And the second question is, how is the water conservation policy structured? Is it a mandatory enforcement that regulates both the utilities distribution efficiency and the community's end use?
That's a great question. I actually don't have all the details on their policy. There was some state regulations that required agencies to back off of to realize savings, but ultimately at the end of the day, it's voluntary with price triggers. So as you have budget-based rate structures all through California, where if you use too much outdoor or indoor, you get penalized for it.
Thank you. Before you go on, thank you so much for your presentation. It was very, very, very constructive discussion. So hopefully we can talk more about this.
Yeah. Yeah, really sorry, you guys. I wish I could stick around and talk longer. I have a client meeting that I need to
No,
get
it
to.
was like the logistic issues. Sorry about
Thank you
that.
so much.
Yeah.
Douglas, thank you, man. Bye,
You're
everybody.
welcome.
Bye, Jamie.
I can stay on a little
Yeah.
longer.
If you don't mind, I wanted to
No,
ask
I don't. I don't mind.
if you don't mind to stay longer to answer some questions, that would be great.
Yeah. So I do see one question in terms of that was directed at Jamie. What cybersecurity measures are you considering for water energy projects? And that is another major issue that the distributed energy resource industry is also having to grapple with. They recognize that is that's a major weak point right now. We have a lot of distributed energy resources that are out there, either on the distribution grid, but this also applies to bulk grid solutions that are using some of the new energy tools where they are exposed to cybersecurity. They haven't taken a more holistic approach to protecting their systems. So that is an active effort. And again, when I talk about West Coast Associates, some of the engineers there were actively working with Department of Energy and other government agencies on cybersecurity. So they're real leaders in cybersecurity for the water and wastewater sector. And it is a top priority for the federal government to help industries across the country, in every sector, to really figure out cybersecurity. We have a lot of holes left to fill.
So, folks who are here, if you have questions, please unmute yourself and ask. Or if there is any comment that you would like to provide.
Doug, I have a quick question.
Sure.
So I know, and Jamie and you talked about reliability, but how do you actually quantify, right? It's very hard to, because a lot of times when you look at these cost of energy projects, they're looking at direct costs, but you have to, in terms of operational. I saw Jamie had a slide where it says operational flexibility, but when you make those investments, there's a lot of reliability or redundancy for emergencies, right? That you need to have, and it's hard to quantify that. How do you, yeah.
So now so let's, all right, there's a difference between reliability and resilience. So it sounds to me you're talking more about resilience, like making sure that you have the energy you need when you need it. So if the grid goes away, is that kind of what you're talking about?
Not only that, for during an emergency, let's say you have, if one of your facility breaks down, right? You still are able to supply. How do you, provide that redundancy to your, so there's, even you're making those investments that, it's hard to
Yes,
quantify.
yes, it is. It is very hard to quantify. So again, it's easier to quantify on the reliability front, and that's um, Oak Ridge National Labs is saying that their models for modeling reliability at the grid scale are out of date, and they can't really do it based on all the things that are changing. So they're developing new models, and one of the key outputs of those models is cost. All right, so the reliability side of kind of calculating this stuff, there are models, there are tools out there to help you assess, what's the cost benefit of making particular investments in terms of providing reliability. When you get to the resilience side of, calculating the value of resilience, that is something everybody is struggling with. It's really, really hard to calculate what's the value of resilience. I refer to the fire here that happened right outside, right up on the hill, the Thomas Fire a few years ago. There was a pump station that went offline after about an hour. Once the fire department got up there, they only had an hour of water use, and we lost some 600 homes.
Wow.
Now, what would be the value of resilience if they had a battery that even gave them an extra hour of protection? No, they wouldn't have saved, 400 homes, but it would have given them another hour of strategic opportunity to save as many additional homes as you can. And, the cost of that 1 hour battery would have been, less than $1 million. Well, that's up on the hill. That's 1.5 homes, and they lost 600. So, how do you calculate the value of resilience? It's a difficult one.
Thank you.
That was a great question. So Doug, do you have redundancies for everything in your system right now, or some of the critical ones do, and some don't, like the example of the pump that you mentioned? So how are they being evaluated, where and how?
Well, the Thomas Fire and a couple of other fires here in California brought this whole issue of resilience up, and also targeted these pump stations that water facilities operated out towards the interface between wildfired zones and the general community. And historically, most water facilities have not provided backup power to those sites. Legislation was passed this year basically mandating that over the next 4 or 5 years, water facilities now need to provide backup energy at those pumps to make sure that firefighters have as much time as they can. Again, not going to guarantee you're going to save all the homes, but the longer you can have water available for them, the more strategic decisions they can make to try and protect as many homes and as much property as they can. So right now it's in flux in terms of that kind of a backup and redundancy. When it comes to a specific an actual water facility, and this goes back to the other question in terms of reliability. Um, if you have an energy system that is providing 80% of your power and the rest you're getting from the grid, and something happens, well, that's why you still maintain your connection to the grid. Um, if your energy source fails, you can at least get additional energy from the grid to keep yourself running at your minimum capacity levels that are necessary to meet your mandates.
That makes sense. We have maybe 2 minutes for additional questions.
Doug, I guess I have a more philosophical question.
Sure.
So, based on your presentation and Jamie's and kind of what we're hearing, things are changing very quickly. And there's like a huge menu of options of what technologies are available. And it's very context specific as well, like where you are located, what type of facility you're managing.
Yep.
So I guess maybe one thing is I think we all know that water utilities are very risk averse and very conservative. So how would you suggest they should, but they're optimistic or maybe do want to kind of be more progressive? What would be the starting point for them? And then I guess us as a more like researchers, where do you see the gap that we can fill in or kind of work on to help that transition?
And this was something that Jamie and I were grappling with when we were at West Joe's, is recognition that it is a very conservative community. And so we came up with a development plan, a project development plan to try and promote our services. 'Cause our goal was to stand up an energy practice at West Joe's, and for a variety of reasons, that didn't go over so well. That's another story altogether. But we came up with a program called Resilience First. And our idea is to target pain points that water facilities have. And the biggest pain point is backup energy. They hate their diesel generators. Everybody does. I mean, you've got a diesel generator. You're not allowed to run it that often. When it does run, you're lucky if it actually turns on and does what it's supposed to do, particularly when the power goes out. More often than not, the generator might come on, but it didn't come on fast enough, and all the switches are thrown. So somebody's getting woken up at 2 in the morning. They've got to go in, they've got to turn all the switches back on, and then connect the generator to the system and bring things back up. So on top of that, the diesel fuel, it has a shelf life. It's about every 6 months, you got to dump whatever you've got in that reserve tank and replace it with new fuel. It's a very expensive piece of hardware that is necessary, but if you can find a better solution. So our pitch was, look, let's bring a battery in and solve that one pain point about when there's bad power coming in and it throws those switches. Why not have a battery there that can automatically come over and take the load, keep the switches from going, send you an alert, and now you've got 2 hours, 4 hours before you actually have to come over to the site and switch over to the diesel generator. And the idea is solve that pain point, get them exposed to the power of renewable energy resources and distributed energy resources, particularly batteries, get them comfortable with it. And what we've seen is we get these installations in, and immediately after they see that it works, they're like, oh, well, what if I use the battery over here for this? And if I do have the solar and it's getting the energy there, they immediately go to, oh, well, then I could rely on this to help me do energy arbitrage. If I've got my solar field, I can get these batteries, use all that solar energy, and instead of putting it out to grid and get pennies in exchange, I can completely offset my evening ramp. Wonderful. So find the pain points and come up with a simple first step. Again, backup systems are just a bane for water and wastewater facilities. Solve that problem, get them comfortable with it, and you're off to the races. Now, we've got 2 examples that popped up here in California where that the system works exactly like that. Both of them were up in San Luis Obispo County. One was at a wastewater plant and one was at a 400 horsepower water distribution pump. Now that one I'll talk about first. They've had constant problem with the quality of the electricity coming through to that pump. And it always throws off a couple of times a week. And they put a battery in there. It automatically comes in, smooths over that bad quality power, and their problem is gone. At the wastewater plant, what actually happened is the battery took over when the power went out one night. It was out for about a half hour. The power came back on, battery went back into recharge mode. But guess what? Nobody even knew it happened until about a month later when they went through and went back through the records. They didn't even know. So that's the angle we have.
Thanks, Doug.
All right. And it's still going to be a challenge, because you're right, they are very conservative. And a lot of the community and across the country, like AWWA memberships are very, very conservative. They are in that camp that just don't believe that renewable energy is going to be able to take over from traditional resources. And it's just going to continue to take time. And I think right now we're heading into a crisis where the increased cost of energy tied with the decreased reliability that the IOUs and the big conglomerates are able to provide are going to make people start thinking outside the box and say, this is not working anymore, guys. We've got to do something different.
Interesting. All right, so I don't see any more questions in the chat, and I don't see anyone who unmuted to ask questions. So I would like to thank you again, Doc, for your great presentation and great insight. This is always very helpful to hear from the practical people who are in the field. So sometimes we researchers get so much into the theory and that we lose sight on the actual work. So it's great to have you guys here and talk about those aspects. And I thank everybody else who joined this webinar. So I hope that we can do more of these to make sure that we are aligned with the actual need in the field.
Yeah, I agree. I'm actually fighting a little personal battle here at the CEC. When I got here, I was quite surprised to discover that 80% of the staff at the CEC came here straight out of grad school and have no real world experience with actually deploying an energy project. And yet they're the ones coming up with the policies and the programs to help. It's just, so I'm spending a lot of time trying to help them appreciate what's going on the ground out in the real world. And so thanks again, everybody. I really enjoyed this, and I hope we can do some more of this in the future.
Yes. Thank you so much, and happy holidays, everyone.
Happy holidays, everybody. Bye-bye.
Thank you.